Welcome to Unit 4, Part 2. Today we're going to do CPU scheduling and first come, first serve, and shortest job first. So just to remember the calculations, we will be working with turnaround time, waiting time, and response time. Only in our situation, waiting time and response time will be the same thing because the processes will only wait one time. So the CPU scheduling algorithms that we're going to be doing are first come, first serve, and shortest job first. So in order to test these algorithms, we're going to use what's called a Gantt chart, which is a timing diagram. And we're going to start very simple with a very simple exercise, and each time we'll get a little more complex. So we have three processes here. We're going to assume that these processes all arrived at time 0 and in this order: P1 followed by P2 followed by P3. And what burst time means is that's the time that the process has on the CPU. So that's its CPU burst time. So we use this Gantt chart, which is the timing diagram, and we start at time 0. So at time 0, all of our processes are in the ready queue, but they've arrived in the order of P1, P2, P3. So the first one to go will be P1. And this Gantt chart represents which process is currently on the CPU. So P1 is going to be on the CPU, and its CPU burst time is 24 time units. So it will be there for 24 time units. And then at time 24, P2 will go and be there for 3 time units until time 27, followed by P3 for 3 time units, and it will finish at time 30. So now we have 100% CPU utilization, and all of the processes only waited one time, so their wait time and response time will be the same, but that will not always be the case. And now, taking our Gantt chart, once we have put the processes on our Gantt chart, we can start to make our calculations. And we're going to calculate per process and then get the averages. So we'll start by calculating the wait time. Assuming that all processes arrived at time 0, P1 waited 0 time units to get the CPU, P2 waited 24 time units to get the CPU, and P3 waited 27 time units to get the CPU. So if you took the average of that, you would get 17 time units is the average wait time. Then we can calculate the turnaround time, where you just find out which time the process left the system and terminated. So the turnaround time for P1 is 24, the turnaround time for P2 is 27, and the turnaround time for P3 is 30. So the average turnaround time using this algorithm, first come, first serve, with these three processes is 27 time units. So because we have the short processes that are behind the long processes, we have what's called the convoy effect. So now we're going to do the same exercise, but we're going to do it with shortest job first. That means they all arrive at time 0, but we're going to run them in the order of the shortest ones in front and the longer ones in the back. So we have P2 will go first for 3 time units, followed by P3 for 3 time units, followed by P1 for 24 time units. So it's the total time it takes is still 30 time units, but this will change the results for the wait times and turnaround times by putting the shorter jobs in the front. So if you take a look at the wait times, we have P1 only waited 6 time units to get the CPU, P2 0, and P3 3. So we have an average wait time is 3 time units for this algorithm, shortest job first, and an average turnaround time of 13 time units, where P1 finished at time 30, P2 finished at time 3, and P3 finished at time 6. So if you compare these averages with first come, first serve, you can see that the shortest job first algorithm has given much better results. So why don't all systems implement shortest job first? Well, first of all, shortest job first has some problems. The first problem is that you really don't know how long a CPU burst is. So a process doesn't come in with the PCB with an item in the PCB that says how long the next CPU burst is. So that's a fundamental problem in implementing shortest job first in a system. Another problem with shortest job first is that since shortest job first is priority based, there is a chance that it could cause starvation. And therefore, it might not be the best algorithm because some of your longer tasks may be important. So there are different reasons, the first one being a fundamental reason, but also starvation could be another reason. But you can, if you would like to have all of your shortest tasks go in the front, there are some ways to implement algorithms similar to shortest job first. The first is that you could assign higher priorities to the tasks that tend to have shorter CPU bursts, so you know what's going on in your system. Those tasks that tend to have shorter CPU bursts would have a higher priority. You could use a multi-level feedback queue implementation, which you don't know what that is yet, but we will be doing that on your CPU scheduler programming assignment, so I will explain that when we get to it. Or you could use what is called the prediction formula, which uses exponential averaging of the previous burst to predict the future. So let's go over the prediction formula. The prediction formula is we're going to be predicting the next burst, which is big T of n plus 1, based on our previous predictions, which is big T of n, and a weight, which is a, and the last burst that just happened. So let's just go over this formula. So big T of n plus 1 is the burst we're about to predict. Little t of n is the last burst that actually just happened. A is a weight between 0 and 1, and it determines what is more important. Well, if A is 0, then big T of n plus 1 is going to equal big T of n, and so that means that the last burst that just happened is not important at all. And if A is 1, then it means that big T of n plus 1 is going to equal the last burst that just happened, so that means all we care about is the last burst that just happened. And this is not just a prediction formula for shortest job first, this is an exponential averaging prediction formula that's used to predict future behavior based on past behavior. Here's an example of that. If you wanted to predict T of 3, you would have to predict T of 1, then T of 2 in order to predict T of 3. And then it just comes down to straight algebra, where you start out with the given information here, and you can algebraically plug in the information. So we will start by predicting big T of 1. To predict big T of 1, we just plug in A, which is 0.25, and multiply it times 3, which is the T of 0, the last burst that just happened, and 0.75 times big T of 0, which is the exponential average system starting value. And we would get that, and then our big T of 1 would be 2.25. Then our next step would be to predict big T of 2. So to predict big T of 2, you take 0.25, multiply it by little t of 1, and then multiply 1 minus a, which is 0.75, times the big T of 1 we just calculated, and you will get T of 2. And then you can take T of 2 and get T of 3. So in this situation, with this prediction formula, it's just a plug-in, and the information will need to be provided for you in order for you to do any exercises involving the prediction formula. But more importantly, you want to understand why the prediction formula would be used, because shortest first is the shortest job first will give the minimum average waiting time for a set of processes, and it may be that the best for your system is to put all of the shorter tasks first, so the prediction formula would be a good way to implement this algorithm without actually having the CPU burst lengths. So thank you very much, and the next video we will be doing some more CPU scheduling practice.